All right. 3, 2, 1. Hey there, guys. What is going on? And welcome to the Evidence-Based Excellence Podcast, yet again, with your host, Mr. George Cresswell. And today we're going to be answering a very, very complex question. That is, are InBody machines any good? A little bit about how they work, a little bit about how they stack up relative to how other body composition methods work, and how accurate they are, how reliable they are. And yeah, it's going to be really, really interesting episode. Going to be diving a little bit into the physics of how the process known as bioelectrical impedance analysis works, and basically an insight into what the machine, whether it be an InBody machine, whether it be a Cited, whether it be any other form of bioelectrical impedance analysis machine that you are using to estimate your body composition, no matter what one it is, pretty much all function the same way. So we'll be going into a little bit about that, as well as how valid and accurate the InBody in particular is the example that I am using today, as it's becoming widely more popular, not only in research and clinical settings, but also in gym and healthcare settings. It seems to be becoming more and more popular of a measurement that gym members are getting access to measure and keep track of their body composition over time. So it's important to know how they work. It's important to know how accurate they are. It's important to know how to test correctly, and a little bit about insight into how the machine works, even if it's just so that you can, amaze your friends and family at the next social gathering or whatever by your knowledge of how electrical signals through a body works to tell them how fat they are. But basically, that's what the process comes down to. In a nutshell, the machine, which typically will look like this if it's an InBody machine, will send signals through the body, or an electrical current through the body at various frequencies, and that will be used then to measure the resistance to that alternating current flow. That's what's known as impedance. That will be measured, and then different tissues will have different resistance and what's known as resistivity values. And the differences in those resistances will allow the machine to differentiate between tissues. As a result, then you get distinct values for muscle mass or skeletal muscle mass. You get distinct values for bone density or minerals. You get distinct values then potentially even for intracellular and extracellular water, potentially. It's one thing that's unique to some of the very sophisticated BIA measurements. But then you also get things like body fat and stuff like that, which is what people are really, really interested in. Typically, when people are doing these tests, they're interested in the body fat to muscle mass relationship. Okay? So that's what these are really, really useful for. So how does it work? So basically, all impedance refers to is the relationship or the combination expressed in various ways between resistance and reactance. Okay? So it's typically used in different ways, and different machines and different units have different equations that they use, but basically it all comes down to this. Impedance is typically expressed in one of the following ways. So it's typically either expressed as resistance and reactance. So you have another quantity or another value known as impedance magnitude, and that's expressed as the square root of R squared, which is resistance squared, plus reactance squared. Okay, this is basically what the machine and the overall maths behind impedance as a whole is in physics. Okay, these are physics equations. And then you also have another quantity known as phase angle, which is how the waveform varies or shifts in either the left or the right direction from a particular reference point. And that is expressed as the inverse tan times by the ratio of reactance and resistance. Don't really need to talk too much about those. That's just basically some of the math behind the values of impedance and impedance magnitude themselves. Bioimpedance, which is what we're referring to when we're looking at it in like a human biological condition, basically with the main focuses we want to zero in on are resistance and reactance and how they are expressed. So resistance is expressed as resistivity times the ratio between length and area. Okay, so the type of material, just think about it, the type of tissue that this electrical signal is going through is given by this resistivity value. Okay, that'll later come into even more of effect when we put in something called a shape factor later for humans when we're looking at one of the other equations. Then you have reactance, which is the resistance to voltage across resistance to voltage variation, across the object, and that is expressed as the following. It's expressed as 1 over 2 pi times the frequency it's going in times the capacitance. Now, all the capacitance is the ability for tissues, particularly non-conducting tissues, which is body fat in human systems or in bioimpedance systems, to store and save electrical charges. Okay, that's basically the idea behind capacitance. So then you go and the machine will work out capacitance. It will then use that value to input into this reactance equation, which you can then use in the resistance and overall impedance equation. Okay, when we're looking at whole body impedance, that becomes very, very important. And then the machine will attempt to work out body volume. Okay, so the overall volume that your body takes up. And that is expressed very similarly to the way resistance is expressed when it was expressed as resistivity and then length over area. Well, now we basically sort of almost take the length and area together, because now we get resistivity times the ratio of the length squared, which is the length is the person's height squared times the resistance. Okay, so that's where we start to look and getting into more body volume. Okay, so we're starting to extrapolate it or put it more into a human construct, so to speak. And when we're starting to get our more accurate measures now. From there, then, it's basically just a case of isolating what component of human body composition makes up what proportion of the overall volume calculated. As I said, the height of the person then replaces L in the length previously. As I said, fat mass is the non-conductor component. Total body water is typically also quite easy to calculate. On average, it typically forms about 73% of the individual's fat-free mass in a hydrated person, okay? And as I said, a large proportion of skeletal muscle mass is water, okay? So then you end up with this value of 0.73, which is 73% times the overall fat-free mass value that's given up, and we can isolate that as water. Okay? We don't necessarily know if it's all intracellular or how much of it is intracellular and extracellular cellular yet, but we then, as I said, go into different measures of how the machine sends these signals into the body. Okay? And this is where we can start getting really down into the weeds of what's going on. So we have something known as single frequency bioimpedance analysis. And single frequency is exactly what it says on the tin. It just sends one frequency into the body. Bioimpedance attained typically from 50 kilohertz electric current. Okay, that's typically what the single frequency bioimpedance analysis technique uses as its current, okay, or as its frequency. It's been one of the earliest proposed methods of how to use this measurement technique. and it's based on the inverse relationship between the assessed impedance and total body water. So single frequency bioimpedance analysis predicts that the volume of total body water is composed of fluctuating extracellular fluid, which represents approximately 75% of the total body water. Therefore, the remaining percentage of the water calculation, the total body water calculation that we derived from that fat-free mass component earlier. Sorry, a bit of a mental block then. If you remember back earlier, we had a component known as fat-free mass. About 73% of that, the estimate will be given to be water. And then about 75% of that we typically see as extracellular water, which will fluctuate. And then the remainder will be intracellular water. Extracellular and intracellular basically just mean inside, extracellular, no, outside and inside the cell membrane. Okay, I got those two confused in my head for a minute. Extracellular, outside, intracellular, inside. And then the thing that separates them is the cell membrane. So it's not infallible. Biggest thing to remember with single frequency bioimpedance analysis, it's not infallible. And it doesn't seem to be valid. And this is one of the limitations of BIA that is also present in other methods as well, is that it's highly variable depending on hydration status. So any individual going under significantly altered hydration, whether it be severe dehydration or severe overhydration, is going to have skewed values, okay, due to these fluctuations in total body water, okay? It also has inherent limitations in intracellular fluid prediction, and also due to just natural differences between conductivity in tissues, person to person, some natural error is present, okay? It's never 100%. No measurement tool is 100%. There's always going to be some natural error there. But all in all, it appears the error for BIA is quite small when all the other conditions are in place as they should be. So as I said, single frequency BIA or bioimpedance analysis just uses one frequency. You then also have multiple frequency BIA. Okay, and this is done in various different ways, but it just involves using two or more frequencies. There's a fundamental finding at the heart of multiple frequency BIA, and that is that extracellular fluid and total body water can be assessed by exposing it to low and high frequency electric currents, respectively. Okay, so this is based on a fundamental finding that is we can better isolate which component is which by exposing it to different frequencies. That's where we get a distinct advantage with using more than one frequency, so then we can hopefully get more accurate measurement tools. That's the idea. More frequencies, more accuracy, more validity. That's basically the idea, okay? Various frequencies have been proposed. You can check all this out in the notes I've left down in the description or in the show notes in the sources, okay? You can check all this out. So, you know, 100 kilohertz and 1 kilohertz have been used, anywhere from 5 to 1,000 kilohertz. Some people have defined it as low, medium, and high. So you have low, which is less than 20, then between 20 and 50 is medium, and then over 50 is classed as high frequency, and these are all in kilohertz again. But the goal remains consistent across all iterations of the method, and as I said, that is to gain greater accuracy in measuring these different components of body composition. That's the idea. In general, it appears that multiple frequency BIA tends to predict extracellular fluid. I was just looking over at my notes to make sure I got the right one, better than single frequency. So that's one distinct advantage that we seem to see. However, single frequency has been proposed to offer more precise results in measuring total body water in populations suffering from disease than multiple frequency BIA. I'm not exactly 100% sure why, but that's maybe a question that we can come back to another time, maybe. Also, multiple frequency BIA tends to show less sensitivity to detecting fluid shifts between the extracellular matrix and the intracellular fluid, at least in elderly and diseased populations. So maybe that's one exploration. Maybe that's one explanation, right? There's a limited sensitivity in fluid shift across the membrane with multiple frequencies. And then depending, therefore, on the sample of analysis will depend on what sort of tool you use, okay? You then have the final method, from my reading at least, as to how bioimpedance works. And this is what I alluded to earlier when I talked about shape factor for determining human shape and making sure that also comes in with body composition, because obviously humans, we're not just a cuboid. We're not just a cuboid of a set volume. We have different compartments. Typically with the human structure, we have 5 distinct compartments. We have 2 arms, we have 2 legs, and then we have our trunk, which includes our head and our upper body. So, and these are not the same as one another, okay? Now, obviously, the arms are similar to each other, but they're not similar to the legs, and the legs are not similar to the trunk, okay? So this is known as bioimpedance spectroscopy, okay? It's where you just use a broad band of frequencies. And from what I've seen from using the InBody machine, this is quite accurate. It uses a broad band of frequencies, and it has 2 absolutes at either end of the resistance frequency scale. You have resistance at 0 frequency, and then you have resistance at infinite frequency. Okay, this is where you start getting into really maths. All fun. But then this is used to predict extracellular fluid and total body water, respectively. Again, harkening back to what we talked about before. Basically, the bioimpedance spectroscopy method employs a variation on one of the fundamental equations regarding resistance, as I said, in order to account for body volume, resistivity, and the height of the individual, while also, this is the thing I was alluding to before, the dimensional or dimensionless shape factor, okay, is what they termed it by, I think it was a researcher known as, well, researchers with the head researcher being called Van Loen, I think. Yeah, I think it was Van Loen and colleagues. Let's see if I can link it down below. But it's high. This is calculated then from the lengths and perimeters of the upper and lower limbs, as well as the trunk, as I said, in order to fully account for the differences in those distinct compartments, okay? That is expressed as the following. So then the resistance expressed as this dimensionless shape factor times the resistance, and then you have the height of the individual squared over the body volume. Okay, that's where this whole idea comes from. They've isolated it to be from the statistical anatomical measurements, is this dimensionless shape factor for an adult human. It's typically around 4.3. Okay. Maths over with, thank God. So obviously you don't necessarily need to know all that. I just find it quite fascinating, and I wanted to talk about it a little bit. I find it quite fascinating. So we're getting on to whole body and segmental bioimpedance analysis. So the bioimpedance analysis comes in many, many forms. Okay, and this is we're basically talking now about the different units that you see that use bioimpedance analysis. Okay, and so you're going to start getting into which one InBody actually is in a moment. So you typically get one of 3 methods that use bioimpedance analysis to measure whole body BIA. Okay, to use it across the whole body and to get a picture of the entire body composition of an individual. You either have hand to foot, foot to foot, or hand to hand methods. Okay, in research settings, hand to foot is the most common and involves placing electrodes on the back of the hand and the top of the foot on one side of the body on a supine participant, and then the signals are sent through the body. The electrodes are then filled with gel in order to minimize what's called the gap impedance, which is a potential confounding variable. And the electrode that emits the current is distal, and is located in the metacarpal or metatarsal region of the hand and foot, respectively, to the voltage electrode, which is located more proximal. So if you basically imagine the back of my hand, distal, let me just hit the microphone. Distal is going to be up here, proximal is going to be more here. Okay, that's basically what that is referring to. Basically, if you can't watch the video for whatever reason, I would describe it. If you look at the back of your hand, distal in what they're talking about here is going to be up towards where your knuckle line is. That's where your metacarpals are. And then proximal is going to be coming back towards the forearm from there to where your wrist is. And that's where that voltage sensor is going to be located, or that voltage electrode is going to be located. So the current is distal, the voltage is proximal. Now, if you imagine that's on your foot, up by your toes where your metatarsals are, not on your toes, on the bones just before the bones that make up your toes, they are your metatarsals. And then further back up the foot towards the ankle is where the voltage sensor then is going to be located. Okay, that's basically a little bit of a description as to what's going on here. Overall, then the test then runs for 15 minutes and it uses all of the methods that we talked about before in the math section. So then you also have foot to foot. Now, this is one you'll see more commonly in more free living or recreational settings. This involves, it's very similar in how it works to the previous method. All of these work in basically the same way, but rather than having somebody laying supine with the electrodes connected to the back of their hand and foot, the electrodes are located in a pressure pad that the person stands on. Okay, if you think about like a smart scales, it's basically the idea of what goes on with smart scales, okay? Not saying that smart scales are particularly any good. In my opinion, the ones you get for very, very cheap, they're not very good. But anyway, so the person stands on this pad like a scales and lines their feet up with the electrodes, and then that's how the electrical current and voltage is sent. Okay, so the voltage electrodes are located laterally, which is towards the outside of the foot on the electrode part of the scale, and then the current electrodes are located more medially, which is towards the inside. So basically, if you imagine one of the sensors is going to be up towards the top of your foot, around the metatarsal region again, the voltage sensor is going to be on the side of your pinky toe, and the current sensor is going to be on the side of your big toe. That's basically the idea. You then have two sensors, again, further back, more by the heel, again, voltage on the outside, current on the inside. Okay, so you still have two distinct electrodes for current and voltage for each foot located in two regions along the foot. Okay, so a total of 4 electrodes really each foot. Okay, and then the last one is hand to hand. So hand to hand uses a device which you may have seen. I haven't really seen a lot of them nowadays. They were sort of older devices that I saw. That you would hold out, that you would have hold of, and you'd hold that in front of you in a horizontal position, and then it would send the electrical impedance signal through your arms. Okay, so the electrodes are located in this one on the handles, and the person before they start, they'd input their height, they'd input their weight, and then that would also give you things like BMI and stuff like that. But then it would estimate your body composition, particularly only body fat, the ones that I used back when I was in college. But it would then estimate your body composition based off the hand-to-hand measurements. It would be the sensors which you hold out in front of you horizontally. So, yeah, there's 3 distinct ways, basically, that it can be measured, depending on the sophistication of the setting that you're in, and depending on what the overall goal is, I guess, of what's going on. So, segmental BIA defines impedance analysis in terms of the 5 compartments we mentioned. So it's your 5 compartments: 2 limbs, 2 arms, 2 legs, 4 limbs, 2 arms, 2 legs, 1 trunk. Okay, so that's what we're segmenting. And this was introduced to overcome the disparity between the trunk resistance to arms ratio and the trunk resistance to legs ratio, which is 0.27 and 0.66 respectively. And the reason these ratios are so poor is because the trunk makes up disproportionately more of the overall body mass than the arms and the legs do. So the assertion is that the trunk makes up about 50% of your overall body mass. Obviously, then you have to split the 50% 4 ways. And that's where you get these disparities in ratios from. Okay, so this is where we end up with segmental bioelectrical and impedance analysis from. And basically, the InBody machines refer to one form in particular. There's 4 different forms, which you can read about down below. But basically, the form that InBody uses, at least from what I could read about them, is what's known as double sides quad current and quad voltage method. Okay. Basically, the voltage and current electrodes are located on the right and left wrists. Now, if you think about it, it's in the hands. The sensors will be in the hands, so the right and left wrists when you use an InBody machine, and then the feet electrodes are obviously located in the scale. InBody machine is a mixture basically of the hand-to-hand and foot-to-foot methods, and they bring them together. Okay, so in the handles you have electrodes that basically work very similarly to the hand-to-hand measurement, and then you also have the electrodes in the scale on which you stand on to use the machine, which therefore use the foot-to-foot method. And so you can sort of almost bring the two together. And that's where you end up with the electrodes in the hands and on the feet, and double quad current or double quad voltage is basically what they step on. What they refer to it as. So now that bit's out the way, how does InBody stack up? Well, you need to ask, compared to what? Currently, the best gold standard method that we have for estimating body composition is known as dual X-ray absorptiometry, okay? That is basically DEXA. That's what DEXA is, okay? And basically, it uses X-rays, hence the X-ray, okay, to get body composition measurements. Very, very useful for looking at bone mineral density. They can also be used to measure body fat and stuff like that. DEXA is known as a 3-compartment model. So it has 3 distinct components with which it can analyze, okay? It's able to quantify bone minerals, fat mass, and then fat-free mass, okay? Those are the 3 that it's able to quantify. More compartments, more sophistication. Some may be able to estimate even more compartments. So as I said, some can differentiate between fat-free mass and skeletal muscle mass. Some can potentially measure glycogen status. You know, as you add more and more things, which the machine can differentiate, or the measurement tool can differentiate, you get more and more compartments, okay? So a lot of BIA, for example, is a 4-compartment model, okay? So as we said before, you get fat mass, you get intracellular, extracellular water, you get muscle mass, you potentially even get bone mineral density, you know. So it's quite a good tool, and basically everything in order to get a measure of its validity and reliability will get compared to the gold standard, which is DEXA. So when we're looking at how it stacks up, when tested, it's compared very well with DEXA for both men and women. So, for example, for body fat percentage, it has been shown to have nearly perfect intraclass correlation coefficient, so 0.98, and also 0.98 for fat mass itself. So if you imagine how correlations work, you have basically 1 is a perfect correlation, okay? 1 is a perfect correlation. So these are very, very close to being perfect correlations. Fat-free mass was 0.99 in this particular study, so it's very, very well correlated with DEXA, okay? So this is good to see. As I said, they also exhibited low standard error across the board in this sample. So you're looking at, it was only off by body fat percentage in the range of about 0.77 to 1%. Okay, so that's not too bad, okay? Fat mass, it was off by about half to, you know, getting up to about 0.9 kilos. So again, there's always going to be error, but on the scale of things, it's not bad at all. And very similar with fat-free mass, again, about 0.6 to 0.8 kilos, okay, standard error. So these errors are quite low. However, one thing you do have to take into account with bioelectrical impedance analysis is there is a systemic error with regards, or systemic bias that does exist with it. And this is common with others as well. And that is that they tend to consistently overestimate fat-free mass and consistently underestimate it. Okay, so it's important to consider. The overall standard errors will be low, but there is a consistent trend for it to overestimate one and underestimate another, which is important to consider even if the overall magnitude is low. Okay, you know, some have suggested that they may also be a potentially useful alternative or favorable alternative if DEXA is not available, to something like a BOD pod, which is known as air displacement plethysmography. There's a source you can check down in the description for a summary of all different body composition analysis tools. Okay, so you should go and check those out if you want to know a little bit more about what a BOD pod is. Okay, but it's just another measurement tool. Okay. There's potential that the InBody or bioelectrical impedance analysis as a whole may be demographic specific. Okay, it may not be useful or valid for all demographics. So we do have a systematic review here of 50 studies that suggested that in adolescents and children, the validity of the results and the measurement error were not satisfactory in this population. So you may want to consider, different demographics and whether it is actually going to be useful. Obviously, we mentioned before that different frequency BIA tools tend to, not have as valid or strong results if used in elderly disease populations, for example. So you have to take this into account. Okay. It may be useful for some, but it may not be useful or appropriate for everybody. Okay. There's many, many other methods that you could use instead. We are able to say, however, that, and this is where we're getting on to one of the big pros of InBody and how it uses the multiple frequencies, is that multiple frequency units, such as the InBody 370 as an example, tend to express much greater positive correlations with DEXA regarding body fat percentage than the single frequency bioelectrical impedance methods. So we have a correlation here of 0.87 versus 0.39. Okay, so there's much stronger correlation with DEXA for body fat percentage in this sample, which was overweight and obese adolescents. Okay. So much stronger correlations with multiple frequency units as opposed to single frequency units. So again, that's another thing which you need to take into account. Body composition analysis tool that you have available. Is it a multiple frequency machine? And as a result, you may get better results and more valid results using that. And you may wish to use it then, for example. A little bit of a illustration of the actual error then that was accounted for. So the single frequency BIA tended to underestimate body fat percentage by 5.5% in this sample, whereas the multiple frequency bioimpedance analysis cut this error down to 1.1%. So hugely, that is significant. Okay, that is very, very significant. So that's almost within the range of the standard error of body fat percentage error that we literally talked about just in the last paragraph about 2 minutes ago. Cut it down to that from a single frequency, which underestimated it by 5.5%. Okay, so the unit that you're using is very, very important to consider. However, InBody does have unique advantages. So for example, it's not hard to do. Okay, it doesn't really require any participation on your part in the sense of you need to be coached in how to do anything. Okay, you step on, you put your details in, you measure your height, you put your details in, the machine will measure your weight, you put your age, you put your sex, and that's it. Literally, the machine will talk you through it. An overall test only takes about 2 minutes. Whereas with something, for example, like hydrodensitometry or underwater weighing, you need to be coached on how to do it, and you need to be able to do that to a certain degree of proficiency. So with underwater weighing, for example, you need, as you're underwater, to be expelling as much air out of your system as possible in order to just get it basically down to a residual lung volume as to eliminate the confounder of oxygen in your system when you're being weighed underwater, okay? So obviously, oxygen tries to bring you back up, and the whole idea is you're being weighed underwater, so it confounds you. That's why you put a weight belt on. It's based on Archimedes' principle. But that can be a very, very big co-founder. And if somebody doesn't know, or somebody isn't coached correctly and doesn't do it properly on how to expel as much of the volume of oxygen out of their lungs as possible as to get an accurate test reading, it's going to confound the test. So if people, as I said, if people aren't proficient in how to do that, then you're not going to get an accurate test. There's none of that with InBody. There's none of that with bioelectrical impedance analysis. Okay, it's just you step on the machine, you put your details in, you hold the handles, and in 15 seconds from the time the test starts to the time it's done. It's done. It could not be easier. It's not suitable for everybody, as I said before. If you have a pacemaker or some other form of internal, heart regulatory mechanism, don't use an InBody. Do not use an InBody if you have one of these things. It is very much so unsafe. Again, whoever's administering the InBody test should be going through these things with you. Again, if you have other things like portesis, if you're pregnant, all of these things, take care. Maybe just use a different method other than a bioelectrical impedance analysis test, okay? Especially if you've got something like a pacemaker, okay? For obvious reasons, it's not going to be good, okay? Then what do we have? However, they are important to take into account the several areas of error that you can get with InBody or with bioelectrical impedance analysis as a whole, okay? So hydration status. Hydration status is the biggest one. So either keeping this consistent in whatever way is going to be very, very consistent, very, very important, sorry, for ensuring good results. Fluctuations in bodily water can easily throw off impedance measurements. You also have prandial state. So depending on whether you've eaten food or whether you've not eaten food, nutrients being uptaken and contributing to your overall body composition in that way is going to impact the impedance measurement. So you need to take into account when you last had your meal and when you're doing the time of the test and all stuff like that as well. Then you also have unit algorithms, okay? So different units have different algorithms, and the different equations are going to produce slightly different results, and that's going to impact the results as well. This can be easily accounted for by using the same unit every single time. So, but again, it's another thing to consider. Another thing you tend to see, how example, is that some units can't take into account, for example, training status and the naturally or the inherent differences in body composition between trained and untrained populations, or between athletes and non-athlete populations, okay? That's something you need to take into account as well. And finally, as I said, the electrode configurations. So whether you're using a hand-to-hand or foot-to-foot or hand-to-foot method, they will probably give you slightly different results. So that's why InBody in particular is pretty good, because it sort of brings the two together. So, but provided you're using the same unit every time, you can account for these. A lot of things you can account for just with consistency, okay? Just with doing the same thing or using the same unit with the same predictive equations the whole time. Okay, so that helps. But how to InBody then? So when we're looking at using the InBody machine, what are the ideals that we want? So the ideals, either you get good sleep, you wake up, you go to the toilet, you remain post-absorptive or fasted, you test naked, and then you repeat under the same conditions whenever the next test is due to come around, okay? Those are the ideal conditions. Now, obviously, a lot of time these aren't possible, especially if you're in a public space, because sometimes you may be in your gym and the InBody unit is located in the gym, and as a result, you can't weigh naked, for example. But also, you might not train in the morning. You might have work early in the morning. You might like to train earlier on in the evening. And if you're going to the gym in the evening, that's when you do your test. You're not doing it earlier on in the morning. You're not fasted. You're tired from work potentially. You've just exercised if you're doing it after training. So there's there's a lot of things to consider, basically. Okay. So how can we negate the confounders rather, as best as possible, and still get you the best result when you can use the machine? Okay. So if you can't do it in the morning, so when testing at your set intervals, let's say you do it every week. Let's say you do this test every week. Okay. When doing your test, if you don't do it in the mornings, just try and do it under the same condition that you can every single time. Okay. So at the same time in the evening, potentially, if it's in the gym, for example, and you get to the gym every time at 6 p.m., then do it every time you get to the gym before you train at 6 p.m. Okay. Maybe you can go to the toilet first and stuff like that when you get to the gym, but around the same time. Then, look at your pre-training meal and make sure that is the same every time and taken at the same time every time. So that way the macronutrient distribution is pretty much the same. So you can negate differences in macronutrient contribution, basically, or macronutrient configuration, okay? And even if, for example, it's a bit like when you're tracking your food, okay? What matters more so if you don't know what steak, for example, to put down as the steak that you've eaten for today, even if it's the wrong entry, if you consistently use that entry for that steak, it will be consistently wrong, and you can still see changes despite it being inaccurate because it's consistent, okay? So, for example, if you always have, 200 grams of chicken and 250 grams of basmati rice and ketchup, or brown sauce or curry sauce before you go training, because that's what you like to do, then do that every single time at the same time before you get to the gym to work out and do your test. Okay. At least then, if your results aren't accurate, they're consistently inaccurate, and you can still see changes over time. Okay. But obviously, the best thing that you could do is be in a post-absorptive state. And then finally, obviously, the clothing that you wear, try and make sure it's the same clothing every single time. So whether it's, a t-shirt or a vest or a sports bra or whatever, other type of gym top, make sure it's the same one every time. Same thing with your leggings, your joggers, your shorts, whatever it is. Make sure they are as consistent as possible so that you're not getting the extra weight. If you wear a heavier pair of joggers to the next test, then that's a co-founder. Okay. If you're wearing your hoodie, whereas you didn't wear your hoodie before, then that's another confounding variable. So you never know, you might accidentally leave your wallet in your pocket, and that's then adding more weight, and your keys are in your pockets and stuff like that. Obviously, if you've got somebody there doing the test, they'll remind you to take everything out your pockets and all stuff like that. But if you can't test as best as you can, literally just your body composition without any clothing, then you just got to do the best that you can. Okay, a lot of this just comes down to doing the best that you can. Oftentimes, not doing the test is better than not doing the test either way. Okay, if it's something you wanted to do. As I said, if it's consistent, if all of these things are consistent over time, then the results will still be more valid than if they weren't. Okay, so just make sure they're as consistent over time as you can to negate these confounding variables as best as possible. So, I said, overall, InBody machines or bioelectrical impedance analysis, very, very valuable addition, potentially, to your body composition, tools, and arsenal. Okay? If you can use them, absolutely, why not? You know, there's no harm in it, you know, unless you're a pacemaker or something like that. As I said, don't use them. As I said, these strong correlations for DEXA, they've been shown to be quite valid, depending on sort of the population and what you use, just the way they're used. Just be careful of the systemic bias, okay? Just understand that they're not perfect, they're not 100%. Understand that there are measurements of error, and that sometimes, if measurements are off, then, it may be due to that under-reporting, but odds are if you're doing things right, they'll be relatively consistent over time, okay? If you're doing things right for whatever goal you want, they'll be quite consistent over time. And you might see little errors here and there. But as I said, if you can't do the test under the ideal conditions, so before you have breakfast, first thing in the morning, after you go to the toilet, in the nude, if you can't do it under those conditions, it's no problem. Just try and do it under the best, most consistent conditions that you can, that you're able to do them under. Same conditions every time. I hope you found that episode useful, guys. I hope that now makes you a little bit more armed and dangerous with regards to bioelectrical impedance analysis, what it does, how it works, and, how you can use it. And yeah, then we'll go over the interpretation of results another time. But yeah, hope you have a good one, guys. As I said, hope you find it useful. And I will catch you next time. Out.